This is the Electron 4 session, and it's probably the most valuable session in terms of the rest of the course. We have a number of things listed here. The first thing about what we learned so far is we learned that for every electron of every atom, there's a unique set of 4 quantum numbers. Now, a quantum number is the way of describing the relative energy and position or shape of electrons in atoms. And it's generalized. It was built on the hydrogen atom, but it's generalizable to all atoms. There are 4 quantum numbers. The first quantum number is called the principal quantum number. The principal quantum numbers go from 1 to 7, and they list the various energy levels. That's the relative distance of electrons from a nucleus. 1, 2, 3, 4, 5, 6, 7, and then when the electron goes to infinity, what it means is it's ionized, it's left the atom. It's called the ionization energy. So the first quantum number is the relative distance of electrons. And the electrons go further and further away from the nucleus, their energy increases. It starts off with a minus value, which is called the potential energy, the ground state of the atom. Okay, the principal level. The second and third numbers, principal level came simultaneously from Bohr's model of the hydrogen atom, and it's really replicated in the quantum mechanics, mathematics from Schrödinger. Principal quantum number is the easiest one. It's the relative distance of electrons. You can have electrons in level 1, level 2, level 3. The second one is called, we'll call it the shape. Now, there's a couple fancy words for it. Is azimuthal. I'll try to list these right here. AZI. Or, very common, angular momentum quantum number. Angular momentum. And these quantum numbers go from 0, 1, 2, 3. And they have letter designations. S, P, D, and F. That's quantum number 2. Quantum number 3 is, I call the direction quantum number. It's called the magnetic quantum number. And the directions, when you have more than one orbital is a space of 2, 1, or 0 electrons. And these are all designated as spaces, like rooms in a house. The magnetic quantum numbers go from, in the case of the p orbitals, 3 directions, and numbers are assigned 1, 0, minus 1. That just designates 3 directions. For D, it's 2, 1, 0, minus 1, minus 2. And F, there's 7 orbitals. The fourth one was identified by Wolfgang Pauli. It's called the spin quantum number, and it's plus 1/2 and minus 1/2. Now these numbers, you don't rank these like an interval number, 1, 2, 3. 3 is more important than 2 or 1. These are designations from the mathematics, and they're dealing with what's called the circular angular momentum of these electrons. And the math is something we're just not going to deal with. Just remember, these designate spaces, shapes. So you put these 4 together. Now you start off with hydrogen, and we're going to start filling hydrogen. The first rule we're going to follow is called the Aufbau principle. It's German. It means fill from the bottom up. If you pour water in the glass, the water goes to the bottom of the glass and fills up. That's all that means. So as we build an atom, this model can be applied to every atom, starting off with hydrogen, atomic number 1, 1 electron. The first electron will go closest to the nucleus. And we'll put a little arrow there pointing up. That means it's spinning about the nucleus, spinning in one direction, obviously. We'll call it clockwise. The second electron, and the designation for hydrogen is it's the first principal level, 1. The shape is called the spherical, quantum number 0 for shape. We'll designate it by letters, small lowercase s, and 1 electron, we'll put a superscript 1. That tells you the principal quantum number 1, the second quantum number shape s, and how many electrons you have, 1. The second electron is helium. It goes the bottom up, it fills, it goes here, and it has to spin in the opposite direction. This is what Pauli determined. When you have 2 electrons, they will couple in a space if they're spinning in opposite direction. It's sort of a magnetic coupling. They create a little magnetic field. Okay, it holds a maximum on orbital, and that's the main concept coming out of the quantum mechanics, that the primary space area that we deal with is called the orbital. And this doesn't, the 0 doesn't, you could put a square there if you wanted to, it doesn't matter. Okay, so this is the 1, helium is 1, s, and then there's 2 electrons. Now the s, this is called the subshell s, has 1 orbital, it's filled. So the next electron for lithium will go in the second energy level, 2, and it becomes, you have the 1s2 already here, then you have 2s1. Then the next electron here, and it becomes brilliant, becomes 1s2, 2s2. Then the next electron goes slightly higher energy level, and this is called the p orbitals now. This is s here, and this is p. And if we had 5 orbitals out here, it would be d, and I didn't draw the d out. Okay, so this would be 1s2, 2s2, p1. That means a p orbital, 1 electron. Now the next electron, instead of going here, it's lower, greater stability of the electron parallel spin. It goes basically 90 degrees away in another p orbital. Okay, now that's called the Hun rule. The Hun rule says when you have equal energy level orbitals, the way they fill is each orbital fills halfway before you double up in any one orbital. So this becomes 1s2, 2s2, p2. And then you see the next one goes here, that's p3, then p4, then p5, then p6. Now notice this, when you get up to neon, is what we have, 1s2, 2s2, p6, or you could say 2p6. Notice you have a noble gas. All the orbitals are filled, all the subshells are filled, and all the energy levels are filled. That's stability. And now you go to sodium, and now you end up with a 3s1. Okay, well, we're going to stop right there, and we'll be dealing a lot more with this.